Hi everyone, in this video I'm going to, using triangles and geometry, prove the triangle inequality, which states that the absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. And just by way of brief background, a while ago a student asked me to prove this result without using triangles and geometry, so essentially an algebraic proof. So if you haven't seen that already, I'll provide a link. And in a comment to that video, someone asked whether I could also now go through the geometric proof. So that's what I'm going to do in this video. Naturally, it's called the triangle inequality. So I think a natural place to start is to draw up a triangle. So I'll just do that now. So let's just draw up any old triangle. It doesn't need to be right angled or anything like that. And eventually we will get the result in this format with A's and B's. Actually, the techniques I'm going to have to use will involve vectors. So actually what we'll see is it's vector A plus vector B is greater than or equal to the magnitude of vector A plus vector B. And essentially the interpretation of this, kind of going back to its name, the triangle inequality, it's basically saying the length of two sides of a triangle will be always greater than or equal to the third side. And this vector notation helps make that really clear, because if you have a basic knowledge of vectors, you'll know that if you take one vector and then add another vector, you essentially end up with a triangle. So we'll get there, but first of all, before jumping to vectors, I'm just going to stick with basic trigonometry. So just to avoid any confusion, I'll label this triangle not A, B, C, but I'll go with X, Y, Z, and that'll just keep all the vector letters different from the normal triangle letters. I'll also follow the convention where the side opposite each point, I'll just label that with the lowercase letter. So opposite point X, I'll call that side X. Opposite point Y, I'll call that side Y, and opposite side Z, I'll call that side Z. So here we have this triangle, and according to the triangle inequality, there's really three inequalities that are true. The first one being that the length of side Y, so the magnitude of Y plus the magnitude of Z would be greater than or equal to the magnitude of X. It would also be the case that the magnitude of X plus the magnitude of Z would be greater than or equal to the magnitude of Y. And finally, we can say that the magnitude of X plus the magnitude of Y would be greater than or equal to the magnitude of Z. So all I've done there is taken every combination of two sides and stated that the sum of those sides, the length of those sides, the magnitude, will always be greater than or equal to the remaining side. Or in other words, that explanation I briefly mentioned earlier, that if you take any two sides, their length will be greater than the remaining side. And it's essentially the mathematical version of saying the shortest distance between 2 points is always a straight line. For example, if I'm going from point Z to point Y, which has a distance X, that's always going to be shorter than if I was to go from point Z to point X and then from point X to point Y. So that's really the mathematical statement that's being made here. Now, in terms of proving this to be true before we then overlay vector notation, we don't actually need to go into a detailed proof of all three of these statements. Actually, in this triangle, hopefully you can clearly see that X is the longest side. And in that case, with X being the longest side, in terms of this inequality, clearly result 2 and result 3 must be true. They're kind of trivial mathematically, because if I already know that the magnitude of X is greater than Y or Z, then if I was to add something to X, the inequality must still be true. X plus something is still going to be greater than Y, and X plus something is still going to be greater than Z if X is the longest side. So really, in the case of this triangle, how I've annotated it, it's really this first result that needs to be proven in detail. So we need to prove this to be convinced that for any triangle we can take any two sides and it'll be greater than the third side, even when we take the two shortest sides their sum will still be greater than the longest side. And the approach I'm going to use to prove this is essentially an approach that Euclid used back when he was proving this. And the way he went about it, he took this side of the triangle Z, what I've called ZX, and he extended it by exactly the same distance as XY here. So in other words, Z. So he's extended this line by a distance of Z such that the length of this line, if I call this point W, the length of XW is equal to the length of XY. So they're both the same. And then I'll just connect W to Y so that we can see that we've both added a new triangle here, triangle WXY, but we've also got now a larger triangle, triangle WZY. But if I focus in on triangle WXY for now, because it's isosceles, we've got two sides having the same length, we can know that the base angles will be equal. So if I was to say give them a name alpha, we know that angle XWY and angle XYW will both have the same magnitude. And therefore visually we can see that the angle WYZ in this bigger triangle, this angle here, that maybe I'll just call beta to refer to, beta is clearly greater than or equal to alpha. It could be equal to if this little extra bit here was 0, or in other words, Z was exactly on X and we just had a straight line. That's where equality would come up in terms of our triangle inequality. But in terms of thinking about, you know, the greater than or equal to, the greater than bit, clearly angle beta is bigger than angle alpha. So now that we've stated that and pointed that out, we can note that in triangle WZY, in that triangle, so this big triangle WZY, clearly we can see that angle WYZ, which I've called beta, so angle WYZ is greater than or equal to angle ZWY. Angle ZWY. Now, in that case, we can conclude that if the angle WYZ is bigger than ZWY, then the length of the side opposite those angles must also be bigger. And that's making use of the result that if you have a triangle, the side opposite a larger angle will also be longer. And I'm just going to make use of that result. I'm not going to rigorously prove that. Although interestingly, the proof of that result also involves a technique of creating an isosceles triangle. But I mean, if I just kind of off to the side here, just draw up a triangle. If I kind of have a triangle like this with a certain angle, if I was to draw a triangle with a larger angle, hopefully it's clear that you can see that the side must then become larger. It's kind of quite an intuitive result, but it can also be rigorously proven. But for this video, because that's not the focus, I'm going to just make use of that. So I might just erase this. But coming back to what we can conclude, we can therefore say that the side opposite angle WYZ, which is side ZW, therefore the magnitude of ZW will be greater than or equal to the magnitude of the side opposite ZWY, which is the magnitude of ZY, which therefore means, if we put in the letters we're dealing with, ZW is the length of Y plus the length of Z. So I can say the length of Y plus the length of Z is greater than or equal to ZY, which is the length of X. And that's what we were needed to prove, so that's as required. So there I've kind of given a geometric proof of the triangle inequality in general. But now what we want to do is, if we come back to our original triangle, we want to think of it in terms of vector notation to then kind of get it into this format that you might more commonly see it, and it's essentially the format that I used when I was proving this algebraically in my prior video. So if I start by thinking about side y, if I think of that as vector A, so I'll call that vector A, and that's the vector going from z to x. And then if I think about side z as being vector B, so that's the vector going from x to y, so if I draw that there, then it's the case that to go from z to y, this vector here, which is side x, is the equivalent of vector A plus vector B. Since if you have a basic understanding of vectors, the way this notation works, if I want to go from z to y, I can go from z to x and then from x to y. That's kind of one of the first things you learn with vectors. So therefore, if I apply vector notation, all I really need to do is where I've got y, z, and x, I can just substitute in the vectors that I've just defined. So from there I can say that vector y, which was at the magnitude of a vector, plus the magnitude of vector z, which I called b vector, is equal to the magnitude of a vector plus b vector. And again, that's as required because that is essentially the format of the triangle inequality that we most commonly see. So there you have it. Hopefully that makes sense and that's a kind of helpful exercise to go through. I think thinking about it geometrically actually helps, I think, have a better understanding of the triangle inequality because it really makes it clear that what we're stating here really is about the lengths of sides of triangles. We're saying that if we take the sum of any two sides of a triangle, that magnitude, that length, will always be greater than or equal to the remaining side, and we have equality kind of in that case where we don't really have a triangle, we essentially have a straight line. So there you have it. Hopefully you found that helpful, and tick boom.